it's very exciting to see increasing interest and, in a way, a structured interest in utilizing POCUS in various streams in healthcare. I think it's a very, very valuable resource, of course. Now, clinically, I work as an intensivist in the cardiac ICUs at the Mount Sinai Hospital, but I am also a card-carrying nephrologist, so I have a little bit of perspectives from both sides, and I also run the AI and informatics program for our Critical Care Institute, so I have some perspectives along those lines. So in the talk today, I'm going to focus on sharing some of the basics of AI, because I think that is critically important for us to get an idea of what goes behind some of these algorithms, to understand how good or not so good they are. And then we'll talk about how some of the studies have so far integrated AI with POCUS. And then we'll talk about future applications, potential future applications of POCUS. We'll brainstorm them together. So the first question is, why do we care about AI? And simply, I mean, AI is pervasive in our lives these days, from different appliances like thermostats to the facial recognition software that you use on your phone, to multiple navigation apps that we use to get from one place to the other, to different text editors, virtual assistants, chatbots, I mean, you name it, and now self-driving cars. They all, to varying degrees, utilize AI. And when AI is this pervasive in our life, of course, we need to know about it. And it's slowly, as you guys know, becoming more and more integrated with medicine. Now, before we dive deeper into POCUS and AI, big question is, what is artificial intelligence? And very simply, it is the science of making intelligent machines. Now, that's a loaded statement, because that begs the question, what is intelligence? And very simply, intelligence is the ability to learn from experience and to apply that behavior to deal with new situations. And it has, many elements to it, as you can see on this very busy slide over here. But taking that into account, we can say that, artificial intelligence is really the ability for a computer to think like a human, simulate human mental processes like perceiving, like reasoning, and most importantly, I think, learning from its experiences, such that it can independently perform tasks that at one point required explicit human input. Now, there are various types of AI that are being utilized today, and they can be put broadly into three buckets. There's machine learning. Then there's this very cool deep learning and NLPs. And I think for the talk today, we'll probably focus more on the first two. NLPs are upcoming in the areas of imaging, but not much in the realm of specifically POCUS yet. So what is machine learning? So machine learning is this technology, are these algorithms that allow the computers to learn on their own based on their experience, without the need for explicit programming. Now, this is important because you still need to program something, but you don't have to give explicit instructions, spoon feed the instructions, spoon feed the actions to the computer. This comes in three different variations: supervised learning, unsupervised learning, and the most upcoming, and something that is my area of interest and our lab is hugely focused on, is reinforcement learning. So what is the supervised learning? Imagine you have this big basket of fruits, and it has some apples, some oranges, some bananas, right? And you tell the computer that, this is how the apple looks, this is how the oranges looks, this is how the banana looks. And now, can you try to separate these fruits out in this basket? So the computer, by looking at these labels, will determine. So here, all we have done is given the computer some labels, but the computer is doing its own job in figuring out that, the distinction is based on color, maybe based on shape, maybe based on texture, maybe based on weight, yada, 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 right? And then it'll come up with this classification where it'll say that, these are apples, these are oranges, these are bananas. Pretty straightforward. Now, the magic happens when we present this model with a new data, with a new basket of fruits, and ask it to now help us identify what's what. And as it turns out, after enough training sessions, when the computer gets good at recognizing what's what, it can do it independently. And this is where, is the power of AI and the power of machine learning. Now, there are a variety of these supervised learning algorithms as you review the literature that come into play, the simplest one of them being regression. So the regression that we all learn about in statistics in a very simplistic way is a machine learning algorithm because we can still automate it. And as we all know, the goal of regression is just to find the best fitting line, right? That's what we do. We try to fit a line in a scatter plot where there is no line. That's regression for you. Now, another important way to do the supervised learning is by something called as decision trees. So these are flowcharts which try to split the classes, these classifications, along the variables that allow for best discrimination between the classes for the outcome that we desire. So in a way, it's trying to produce these different classes with the most homogeneous groups with respect to the target variable. So for example, say I want to go play golf, right? And one of the important things for golf is how the weather is. So I'm going to check what the weather looks like. And where I live, if it's cloudy, then, usually I can go out and play golf. So that's very easy classification that if it's cloudy, I can go play. But as it turns out, when it's sunny, it can also get pretty humid. We'll live near the coast. And if it's also very humid, that's kind of not a good idea to go and play golf and enjoy the game. But if the humidity is low, we can go out and play. But what if it's rainy? Then we need to see, how windy it is, because I can always use some umbrellas or golf carts to still go out and play if it's not too windy. But if it's too windy, then I can't go and play. So this creates this decision tree for the outcome that we need, which is going out and playing golf in this case, for a specific place where I live. Now, say I visit another place and I want to see if I can go play a game of golf over there. Well, as it turns out, maybe I'm in Seattle or maybe I'm in London, where cloudy usually means that it's going to pour and I can't play, right? So these intricacies start to build in. So as it turns out, if I'm using just one decision tree, it is really focused on the data that it was trained in, which is where I initially wanted to play. So it's a model that has overfitted to the original training data. So to counteract that problem, what we can do is we can take a wide variety of data from the database, and we can split it into different segments randomly. And we can just train these decision trees in these different subsets of data. So we train these multiple decision trees all randomly with the idea that they are going to overcome this bias if we were to take all the training data altogether. And this is something that's a very, very powerful machine learning technique called as random forests. Now, another way to approach this is that, we build a model and we've developed this decision tree, but whenever you develop a regression, you'll find some error bars over there. And then you develop another model on top of it to try to reduce those error bars, right? So here we go by something called as entropy, which is essentially like least square errors in a regression. And after we have developed a model, we make another model using that data to try to overcome that issue that with the entropy in the model. And we continue to do this till we get a model that we are happy with. This is a technique, again, a very, very powerful technique to create these ensemble of trees something called as gradient boosting. So we can either develop a random forest or we can develop a gradient boosted method. All right. So moving on. Now, let's say you are particularly feeling adventurous and you're like, I want just to see how good the computer is. So I want the computer to take this basket of fruits that I have and provide me with the subgroups of foods or fruits that are in there, but I'm not going to tell the computer what fruit is what. Let's see what the computer can do. So this is something that is an example of unsupervised learning because you're not supervising what the computer is doing. You just let it run, let it go wild. And as it turns out, there are very, very powerful algorithms which can still look at this basket of fruit and be like, there are some fruits that are reddish, some orangish, some yellowish, some are more round shaped, some more pear shaped, some more elongated. Their weights are different, their textures are different, and it can come up still with these classes of fruits. Now, the computer will not know what's an apple, what's an orange, what's a banana, because we haven't provided those labels to the computer, but it can still do a pretty decent job in identifying these separate classes of fruits. Now, the last in the machine learning category is this thing called as reinforcement learning, which I think is a very, very powerful algorithm, which is also something that is used in autonomous vehicles. And the easiest way to, I think, or the easiest analogy to understanding this algorithm is, a kid trying to learn to walk. So say this kid, his or her parents wanted to go from this table to the chair. What will the parents do? The parents will ask the kid to get up and walk, right? The kid gets up, takes a step, doesn't fall, so gets accolades from the parents. This is positive reinforcement. So kid did something good with how he or she took steps. So now the kid is going to try to replicate that by trial and error. Takes another step, does well again, gets more accolades. What if next time the kid takes a misstep and falls, the kid gets a boo-boo? That's negative reinforcement, right? Kid gets up, walks again, positive reinforcement. So with this trial and error, the kid learns to walk. And if you think about it, this is how you and I learn to do anything in life, right? Including practicing medicine. A lot of times it is trial and error during our trainings and through the life and how we are getting better, in acquiring images and interpreting images for POCUS. This is a lot of it is by trial and error. That is the natural human way of learning things. And that is exactly what reinforcement learning replicates, which is why it is such a powerful algorithm. Now, moving on to deep learning. So deep learning is a concept that is built on the concept of artificial neurons or concept of biological neurons. So just like, biological neurons take input, they will process them and come up with an output. We have an artificial neuron, which is also called as perceptron, depending on, the literature that you look into, that will take some inputs, process them, and come up with an output. So that is the architecture it is trying to replicate. Now, if you look at this artificial neuron closely, it is a very, very simple architecture in a way. It's just a mathematical function. Now, I have to caution you that, most of artificial intelligence is filled with the linear algebra and calculus. That's the way to get into the heart of artificial intelligence, unfortunately. Now, here, what happens in this artificial neuron is that when it gets these inputs, say, we're trying to, again, develop a artificial neuron network for, or a deep learning network for, classifying that basket of fruits. So it's taking these inputs, the color of the fruit, the shape of the fruit, the weight of the fruit, right? Now, the model doesn't know anything about anything. So it still knows the labels, but it doesn't know anything about what input variable is something that is more useful for classification. So it's going to just weight those inputs randomly, which means that it is going to start assigning importance metrics to each of these variables in a random fashion, right? So for example, here the model weighted the input number 2, which is color in this case, more heavily. So the model here, this neural network is going to rely on predominantly color as a way to classify. But again, this is all random, which is why these models have to go through multiple, sometimes hundreds of iterations to try to perfect in what they are trying to do. Now, after this, what it simply does is it takes a sum of all these weighted inputs, and then that sum goes into this function called as fx, which is the activation function, in which we have programmed two things, which is what we do. One, we program that when this neuron should fire, right? So if the value of the weighted sum is more than the threshold value that we program in there, the neuron will fire. Otherwise, the neuron will not. The second thing is, how should the neuron fire? What is the output we are looking for? Now, the output could be, different things. The output could be just a binary 0 and 1. It could be something in between. It could be, some other fancy functions like a ReLU function or softmax function, which, are all utilized for different purposes in artificial intelligence. But this is a very, very basic structure of an artificial neuron. Now, you put these artificial neurons, you stack them up together into an input layer, a hidden layer where they do all the processing, and an output layer, and connect all of them, and you get a multi-layered perceptron or an artificial neural network. You increase the number of these hidden layers, and you get that coveted deep neural network. So it's not rocket science. It's a very, very simple architecture, and you just keep building layers of it and experiment with them to see, what works. Now, when we're talking about POCUS, I think it's important to understand how in the realm of our AI, we read images. Now, say this is a chest X-ray that we want the machine to read. The way the machine will look at it is it will break it down into these small grids of pixels. And then through this architecture called convolutional neural network, it will try to read this image. What it'll do is it'll take a big magnifying glass and start going through some of these pixels. And it will start to extract what it thinks. Again, it's all random. That's why we have to do multiple runs of these. It'll start to extract features, what it think are important. It could be, maybe it's extracting different hues of color. Maybe it's extracting different hues of texture, different hues of shape, different hues of weight. And that is where the black box thing comes in, because you don't know what it's extracting over there. But it extracts those features, puts them into a box of its own. And it does that. It takes that magnifying lens and goes through the whole thing and develops this convolutional layer where it has a blueprint of all these features. Then it takes the next step. It further consolidates all these features that it has extracted into another layer, something called a pooling layer. And then it runs, as I was saying, multiple of these convolutional layers and multiple of these pooling layers to come up with what might be a reasonable output. So it will, each of this layer sends an output to the final layer where they come up with an average of what the final determination is. And we see that as an output. And, the model will be able to tell you whether there was an infiltrate on that chest X-ray or not, for example. And if not, then, it goes through, again, multiple loops of training. So these are loops built into the loops of multiple loops of training. So as you can see, it can get pretty resource intensive pretty quickly. And there are newer models out there now, which I won't go into detail for lack of time, where we can use these transformer architectures or large language models to try to read some of the various imaging modalities. Now, moving on to why do we want to use AI in POCUS? Well, the simple answer is that POCUS is a very user dependent technique. For one person, point of care ultrasound could be a piece of cake, and it could be the bane of existence for the other person. And even for people who are good at point of care ultrasound, if you have 3 different people try to acquire images and interpret those images, you'll get some inconsistencies, right? And it all is based on their expertise, their own niche that's their own practice patterns. So this is something that, the more you do, the better you get. And those are the things typically where AI excels. So it's a perfect place for utilization of AI. Now, one of the most important areas where AI has been used is for enhanced image acquisition and interpretation. So, for example, this is a study from Israel where a human POCUS expert acquired images using one of the point-of-care ultrasound machines, which was powered by AI. And that person acquired apical four-chamber views. And the beauty of the software in this machine is that not only does it help the user identify the best view possible, you still have to be able to get some view, but then it can help you refine the view so that it can make its calculations. But once it identifies the view, it automatically marks out the LV outline in both end diastolic and end systolic phases. And it can calculate the EF automatically. Now, here, when you look at the kappa between the expert and the AI, it's not great, right? It's only moderate level of agreement. So I would take this with a grain of salt, right? But this machine also has the capability of doing an auto VTI with an apical five-chamber view. And with that, the intra-class correlation coefficient was pretty good. But it's a small study, 32 patients, and one against one expert, right? And as we know, POCUS is very user dependent. So I would, take this with a huge grain of salt. Now, moving on to, utilization of point of care ultrasound in lungs. So for pulmonary edema, this is a study that was done at the ER at Rush in Chicago, where the clinical ultrasound fellow in the ER, who was early in their training, was asked to perform point-of-care ultrasounds for pulmonary edema using the 12-zone lung ultrasound technique. And 71 patients in total got done. And then the ultrasound fellow and the AI both read the reports independently, which were then reviewed by two experts in the field. As you can see over here, AI doesn't do that great. It has a pretty good sensitivity. The specificity isn't that great. So, and the reason being that the AI tends to overcount the number of B lines. So the crux from here is that, if the AI says that, the lung looks clean, there's a good likelihood it's clean. But if the AI says there is a problem, there may or may not be a problem, right? So there's going to be high negative predictive value and low positive predictive value. And that's a theme that, you'll see in some of the studies I show you. Now, this is looking at pneumonia at the Children's Hospital in Indiana. Here, there were 7 learners, combination of ER residents, pediatric ER fellows, and they did a blue protocol to identify pneumonia. And then AI made the diagnosis, which was then, and 2 experts independently made their diagnosis against which the AI was benchmarked. And as you can see over here, the positive predictive value, again, wasn't that great, right? Now here, what is also important to note is that out of the 32 patients, only 3 had pneumonia. So again, very, very small sample sizes to hang your head on and if this is a good technique or not, right? Now, this study was performed in Germany and Greece, where the authors wanted to see how well an automated program for DVT detection does in comparison to experts. So each patient was scanned by non-experts, which included a combination of nurses and physicians who hadn't ever been exposed to point-of-care ultrasounds, and expert sonographers. And then things were reviewed, by an expert. And as you can see here, the software again allows not only identification of the right point where the compression should be assessed, but if the software thinks that the compression is not appropriate, the vessels are not exactly centered, it will prompt the users to make corrections. They can always override anytime, but it prompts users to make those corrections. And as you can see over here in the last two rows, the negative predictive value of this technique was pretty good across throughout the reviewers and in the pool data. The positive predictive value, again, not that great. So again, in all these studies, the theme that emerges is that if the AI is saying that there isn't a problem, it might be true. Again, with a grain of salt, because all these studies are very small single center studies. But if the AI is saying there's a problem, that may or may not be true, even with these studies that we have out here. Now, another area where I think AI has shown to be very useful is in training the learners. And as you saw in some of these studies, but this is a randomized trial which was performed at Stanford recently, where they took 43 internal medicine residents who were new to point-of-care ultrasound, randomized half of them to an AI device, half to non-AI device, and asked them to take a apical four-chamber view in a standardized patient, then send them home with those ultrasound machines and said, do whatever you want with those ultrasound machines, practice, not practice, gave them some resources to learn, online resources, modules on point of care ultrasound, and then asked them back in 2 weeks to again rescan that standardized patient in that apical four-chamber view. And as you can see over here, at the baseline scan, there was really no statistically significant difference in time to scan between the AI group and the non-AI group. But on follow-up, the AI group was able to scan those patients much quicker. And the improvement in the scan time was much more impressive in the AI group versus non-AI group. And the image quality as assessed by experts was also much better in the group that was using AI technology versus not. So this is a randomized trial that hints at the idea that maybe a great way to use these technologies would be to train the next generation of clinicians. Now, finally, just a little bit about the future directions. So I think one of the most important things with how I see this evolving is that there will be more and more technologies available for real-time AI-guided probe placement. Especially, if you use things like reinforcement learning, which can in real time provide you a more meticulous guidance in how to place the probe. And not just for apical four-chamber, as most of the studies have been, but for different views, and not just for views, but for the entire protocols like EFAST protocol and whatnot. And if we can do this, I don't think it is a stretch to think that there will be a time where we can ask patients to perform point of care ultrasounds and share those images with experts for their opinion. Similarly, a lot of these imaging can be enhanced in settings like tele-ICUs, where it can be done by novices in the area while using AI augmented techniques for probe placement and image acquisition. And then it can be reviewed by an intensivist who is, sitting either in a different location or a different institution. Another, I think, area where there is a huge potential for this technology is AI-guided needle placement. I work with so many advanced practice providers, fellows, residents, and the hardest part in putting a central line is hitting that vessel. And I can totally see where AI can identify where the needle tip is and can help the user correct the course to effectively and efficiently cannulate the vessel. And this opens up so many potential avenues, right? From arterial lines to central lines to ECMO cannulations to heart catheterizations. I mean, you name it. Once you have access to the vessel, the world's your oyster, right? And finally, this is something that I am very interested in. As I told you, our labs works with clinical actions with machine learning. And I think ultimately AI is a tool and POCUS is a tool. Ultimately, what we need is to take clinical actions. And as folks who do point of care ultrasounds rather than radiologists, our goal is not to generate images and read images for other people to act on. Our goal is to acquire images, interpret them for actions that we can take right then and there at bedside. And combining the power of AI for image acquisition and identifying actions, I think is going to be an active area and a very, very exciting area in the next few years. Thank you all.